As we've discussed enzyme inhibition, what has become clear is that in all cases we have some form of the enzyme, whether it's enzyme or an enzyme substrate complex, reacting with an inhibitor to form this enzyme inhibitor complex. Okay, so the very last thing that we want to be able to do is to determine an equilibrium constant that can tell us how well the inhibitor binds to the enzyme. And similar to what we figured out with the enzyme binding to the substrate, what we really want to focus in on is the dissociation of the enzyme inhibitor complex. So in this case, the dissociation of this is going to end up being a Ki value. Okay, so Ki, just like Km, describes how tightly a molecule, in this case an inhibitor, binds to the enzyme. So this is going to be in concentration units, so millimolar or micromolar or nanomolar. Okay, and the larger the value, the lower the affinity. Okay, so just like Km, this value, this concentration, is the concentration of an inhibitor when 50% of the enzyme is EI, right? So it's the concentration of an inhibitor when 50% of the total enzyme is present in the form of the enzyme inhibitor complex. Okay, so the way that we figure this out from experimental data is to measure Km and Vmax without inhibitor, so no inhibitor, and we also want to measure Km and Vmax with inhibitor. Okay, we're going to call this Km prime and Vmax prime. So these values are determined in the same way as without an inhibitor, but we're going to see that they change based on the fact that the inhibitor is there. Okay, and then the way that we're going to figure out what Ki is we're going to compare these values. Okay, and they're always going to be related through a term called alpha. Okay, so in this case, alpha is equal to 1 plus the concentration of an inhibitor divided by Ki. This is always true for alpha. Alpha equals 1 plus the concentration of the inhibitor divided by Ki. Okay, so the only trick is then to figure out how to apply alpha. Okay, and this really boils down to thinking about the relationship between Km and Km prime, or Vmax and Vmax prime. So for example, for a competitive inhibitor, right? So if we have a competitive inhibitor, we know that Km prime is larger than Km, meaning that we could set up an equation where Km prime equals alpha times Km. So if we know Km prime and we know Km, we can solve for alpha. And then if we know the concentration of our inhibitor, we can figure out Ki. All right? This changes a little bit if we're dealing with, let's say, a non-competitive inhibitor. So for a non-competitive inhibitor, remember we said that Km stays the same, but Vmax for the inhibited reaction is less than Vmax for the uninhibited. So in this case, it must be true that Vmax prime is equal to Vmax divided by alpha. Okay, so whenever the inhibited value is smaller, it's always Vmax divided by alpha. If the inhibited concentration is larger, it must be that the uninhibited value times alpha. Let's see a couple examples of this. Okay, so our goal here is to determine Ki if we know the concentration of inhibitor is 10 millimolar and we have this experimental data. Okay, so this plot is with the inhibitor, this plot is without inhibitor, so there's no inhibitor here. Okay, so the very first thing we want to do is figure out what type of inhibitor we have present. And the slope and the y-intercept will give it away for us here. what we first notice is that our y-intercept values are the same. And if the y-intercept is the same, since b equals 1 over v max, then v max must be the same. Okay? But our slopes are different. So our slopes are different, and we know the slope is km divided by v max, so we must have different km values. So in this case we have the same v max, but different km's, so this must be a competitive inhibitor. So we can set up an equation here where km prime, the inhibited km, is equal to km times alpha. And we know it's this relationship because for a competitive inhibitor, km is larger than when there's no inhibitor present. So then our task now is to use this experimental data and figure out km and km prime. Okay, let's start with the uninhibited reaction here. Okay, my y-intercept is equal to 0.0033, and this equals 1 over v max. So v max must be equal to 303, and this unit is millimolar per second. And I know that because that's the unit of my initial velocity. Okay, so the slope is equal to 0.0333, and this equals km divided by my Vmax value. And my Vmax was 303, so I end up seeing that my km is equal to 10. Okay, so km here is equal to 10. I want to do the same thing with the inhibited reaction. So I'm now going to focus, I'll change colors here. So I'm now going to focus in on this equation. The y-intercept is the same, so Vmax is the same. So Vmax when inhibited is 303 millimolar per second. Our slope is 0.081, and this equals km divided by Vmax, and our Vmax was 303. So when inhibited, this is km prime, we end up with a km of 24.5 millimolar. So we're now in a position to go ahead and calculate what alpha is, because we know that km prime, which is 24.5, equals km, which is 10, times alpha. So alpha equals 2.45. So we now know alpha. And since we're told the concentration of the inhibitor is 10 millimolar, we can go ahead and just do one more step here and figure out what the Ki value is. So we know alpha equals 2.45, and as we discussed earlier, this equals 1 plus the concentration of an inhibitor, which is 10 millimolar, divided by Ki. And if you go through here and solve for Ki, we see that Ki equals 6.9, and the unit is the same as the concentration, so millimolar. So this inhibitor will interact with the enzyme with an affinity of 6.9 millimolar. Okay, so let's look at one more example here, and this one I'm going to work through much more quickly. Our goal is to do the same thing. We want to determine Ki, and the concentration of our inhibitor is still 10 millimolar. So the first thing that we want to do is compare our slopes and our y-intercepts. So our y-intercept has changed. Our slope has also changed. So if the slope and the y-intercept has changed, this must be a non-competitive inhibitor. And remember above, we said that with a non-competitive inhibitor, Km doesn't change, but Vmax does. And it decreases. So Vmax prime, which is the Vmax when it's inhibited, is equal to Vmax, the uninhibited Vmax, divided by alpha. Okay, so our task then is to figure out Vmax for the inhibited reaction and the uninhibited. So for the inhibited reaction, so Vmax prime, it's 1 over our slope, which is 149.3 millimolar. The Vmax for the uninhibited reaction is 1 over this slope, and this is the same as we saw before, 303 millimolar. So 149.3 equals 303 divided by alpha. Alpha, which is our competition factor, is equal to 2.03. So then 2.03 equals 1 plus the concentration of inhibitor, which is 10 millimolar, divided by Ki. So going through and solving for Ki, we see that it's equal to 9.71 millimolar.